This episode documents the data to be used in my molten salt reactor simulation. I'll cover where it came from and what I did to make it fit for use. The end game is to have data adequate to analyze fission product evolution. I'll be using data from the Internet and Microsoft Office products. First, I'll describe the data, including its flaws. Reformatting the data wasn't as hard as deciding what the format should be. Quality control is mostly about finding gaps in the data. At the end, I should be ready to release these data in formats suitable for analysis by others. The nuclear data comes from three major sources. The first has the best graphics. The half-life data is already in Access files. The same source also provides branching ratios. However, the branching ratios data lacks one mode of decay, so I added some data from Geneva. I also got a list of elements from Jefferson Labs, but you can get that anywhere. I imported the Tori 2 data and named my copy Tori 3. I changed some table names and some key field names. I deleted some fields I don't need, such as abundance, and all the HTML strings from which the data were derived. The meta field is new. An isotope can occupy as many as 4 energy levels above the ground state in the current data. I will also add a source field to all the raw data tables. The most important difference between the Tori 2 parents table and my isotopes table is the primary key. They use a code called ISA, an isotope with a Z value of this and an A value of that. It uses a fairly complex equation to turn those values into an integer that uniquely identifies each isotope. That code number is the primary key that identifies the isotope in all of the other tables in the Tori 2 database. I'm throwing out the whole ISA integer scheme. A key value needs to be unique and unchanging, but isotope names are both. Plus, they are far more readable than a code. The isotopes table now looks like this. I keep the ISA code in case I want to reference any of the other tables in the Tori 2 database. With those changes, the original Tori 2 parents table becomes my isotopes table. The atomic weight translates directly. The atomic number Z is actually redundant if you know the element. I put that in a separate table because I still need it for sorting. The element's symbol, not the atomic number, will be used across all the data tables. Data for the new meta field is derived from the ISA code. The half-life data will be consistently measured in seconds. Note that I'm calling the combination of atomic weight, element symbol, and the metastable state an isotope. Actually, an isotope in a metastable state of heightened energy is still the same isotope. The use of 3 keys replaces a structure described in previous episodes, which concatenated these 3 pieces of data, or sometimes just 2, into one isotope name. The branching data starts with the strangely named Parents 2 table in the Tori 2 database from Lawrence Livermore. It has some redundancy that I stripped out. An isotope can decay by more than one mode, so decay mode is an additional primary key in the new branches table. Again, I separate the ISA code into readable components. In modes DCID and SPEC are all redundant. The important part is the decay mode and the percentage of isotopes that take that route. The Tori 2 data does not mention the possibility that a parent isotope can decay to a metastable form of the daughter. This type of decay is the key to creating the popular medical isotope 99 technetium M1. The shorthand decay mode for this is beta-M, at least in the Jeff report. Report 6287 is only available in locked PDF format, so I entered about 100 new records here by hand. That is the most likely source of errors so far. Brookhaven maintains the Sigma database. The relevant drop-down selection is neutron-induced fission data. From there you can select from 14 possible fuels. Most pages include separate paragraphs for slow, fast, and superfast neutrons. All in all, 30 combinations of fuel and neutron energy. I'm calling those the 30 files. The big problem is that each page is formatted for readability on a computer monitor, not for feeding into a database. There are 2 tables here, side by side. The table on the right needs to be moved under the table on the left. Some of the metadata is found in the header. The fuel name is in the web page name. A robust table design will repeat those items on each record. Both the energy and the fuel become primary keys. The isotope designator here is in 3 parts. I need to translate the value for Z into a 1 or 2 letter symbol. A and FPS translate directly to atomic weight and meta. The new field, source, is for documentation. Most of the time it will read sigma, the name of the Brookhaven database, but there are gaps. Some of the decay chains need stable terminators, most likely because the yield for those isotopes is 0. That won't work for me. The database now consists of 4 tables of nuclear data from 3 U.S. national labs and the International Atomic Energy Agency. These tables should be in the first normal form. The database also holds queries to build and populate these tables and to do some quality control checks. Those queries are made easier by relationships, and the keys reduce errors in loading and editing. The first major task involved the addition of the IAEA branching data to the Livermore data. Any new isotopes that resulted from that had to be integrated into the other tables. The first round of quality control deals with internal consistencies within each table. Then the consistency between tables needs checking. The first rule in a relational database is that every record must be uniquely identified. This means that no parts of a multiple field primary key can be null, at least in access. This means there is a G for the value of meta for every isotope that's in the ground state. That takes some getting used to. The user can add additional restrictions, such as the atomic weight always being a positive number. Mostly these restrictions catch errors at the time the data are loaded into the table. They also catch errors in records that are added by hand. In particular, the 3 keys catch any attempt to add a duplicate record. These restrictions can catch mechanical errors, but the numbers can still be wrong. For that, I find Excel more flexible. I can easily export a table directly to Excel, but I almost always want one more piece of information, the atomic number. For that, I need a join to the elements table. This query is copied from the Create Query panel in Access. I always paste the query in a separate worksheet of a new spreadsheet, just as soon as it seems to work. To see if it works correctly, I paste the data it produces into the spreadsheet and start my inspection. In Excel, I paste the query, then the data, then save. The first QC check looks for holes in the data worksheet, using the control down and control up arrows. If you don't know that little trick, learn it. With the control key pressed, an arrow key will move the focus as far as it can within the current block of data. If there is a gap, it will stop. Here, it didn't, so I have no obvious gaps. Then I turn on the filter and look at the range of data. For the atomic weight column, I see the numbers from 1 to 271. Okay. For the symbol column, I only see 1 and 2 letter element names. For the meta column, I see G and M1 through M4. For protons, I see 1 through 109. Some of the newest elements are missing, but they are nowhere near fission products. For half-life, I see 0 through 10 to the 35th seconds, which is Livermore's idea of stable. At this point, I create a pivot table. Actually, nothing much interesting happens here in the isotopes table. I do look at proton number and symbol together. Scrolling down, I see no misnaming. I can examine the number for each meta value, and I see only one element that has 4 energized states. Just for curiosity, I go back to the data and filter for M4. It's polonium. For the initial yields table, you can assume I did all the grunt work, so we'll skip to the interesting part. First, 32,000 records result from the query. In an Excel pivot table, I put fuel in the rows and energy in the columns and had yield as the data. Here are the total yields for slow and fast neutrons for the 14 fuels provided in the sigma data. All of them add up to 2, which is proper since 2 atoms come from each fuel atom that is split. As for the apparent accuracy, 5 decimal places, when some of the data has uncertainty of 50%, I have no comment. The branches table is already fixed. To document its problems, I had to query the original database and put that in Excel. First, there are dozens of really strange decay modes we don't need to see, especially among the artificial isotopes. These are the ones that matter. Right away, I found some gaps. Fortunately, the data from Geneva was available, and as painful as that was to hand jam into the database, there was a worse problem, revealed at the very top of the first pivot table. Recall that the Livermore data uses a numerical code that I replaced. The problem with 8 helium and every other neutron emitter is that the totals don't add up. I'm sure physicists have a reason for this, but it won't work for me. Making sure the branching ratios all added up to 100 was a significant effort. While doing that, I noticed a new mode in the Jeff data, B-MN. Where's that in the Livermore data? The B- means it emits an electron. The N means it emits a neutron. The M means it does not decay all the way down to the ground state of the daughter. There are other decay modes that hang up at an in-between energy level as well, and they are all missing from the Livermore data. The missing modes are available from the international community. Unfortunately, it's in a locked PDF file, so no cut and paste. As you might guess from the multiple items crammed into each cell here, cut and paste would only have been the start anyway. The 2 rows of data here become 5 records in my branches table. 4 of them should already be in the Lawrence Livermore data. Oops, there are only 3. The NUDAT site also lacks IT data. Well, the Jeff data didn't add up to 100 anyway. For 84 germanium, the Livermore data does have a beta-N decay percentage of 10.8, so that's good. As mentioned before, the accompanying beta- percentage was 100 for neutron emitters, so this is the second time I fixed that number. The important part here is that the new beta-M decay mode generates a new record in the branches table. Secondarily, the new record leads to a possibly new daughter product, in this case 84 arsenic M1. Has Livermore ever heard of this stuff? Or of any of the approximately 100 possible new metastable isotopes resulting from the Jeff report? I slipped over to Excel to find out, but I could have done all this in Access a bit more elegantly. The third missing items query asks if there are any isotopes in the branches table that aren't in the isotopes table, because we're going to need their half-lives eventually. If some are missing, we need to add them. I also went back and rechecked to see if all the yield isotopes have half-life and branching data. I can assure you this isn't just the second time those queries were used. Finally, we get to the check we have been aiming for all along. Do all the branching ratios add up to 100%? There are a couple of rounding errors, but otherwise, yes. In conclusion, I made a major change in the primary key with respect to previous episodes and the original database imported from Lawrence Livermore. That database, after a bit of reformatting, provided the raw half-life data numbers and most of the branching data. The yield data came from the 30 files of the Sigma database at Brookhaven. I did a variety of quality control checks, hopefully enough. At any rate, I'll be publishing all of these in a format suitable for importing into a database. I'll also include a composite view suitable for Excel. There are lots of interesting insights waiting for a data miner to find. If you're really adventurous, you can try to recreate my title graphic.